Austin, that makes four. Ohio, Cleveland. I think there are two people from Ohio in here that I know of so far. Silicon Valley, welcome, Jerry. Houston, hey. I wonder who, if anybody's in Houston for Exponential. I'll be there tomorrow if you are. Delaware, Knoxville. Love it. All right, we're going to go ahead and get started. Feel free to keep chatting. Okay, Wade, you'll definitely have to hit me up at Exponential. I'm going to kind of be incognito. I'm not speaking or anything. Um, but yeah, so welcome to the 66th episode of HYSKY Monthly. I can't believe we're on 66, and I also can't believe it's May already, but what do they say? Time flies when you're having fun. I should also say it's an exciting day around our house today because those of you that have been here for at least a year, you'll remember a year ago, my grandkids, twin grandkids, were born on this day, and they're turning one today. So I can't believe it's already been a year since that. That's crazy. So today we're having Philip Stuckey, Dr. Philip Stuckey, present on recycled precious metals for fuel cells and aviation, deadheading of platinum. Now, don't worry if you don't know what that means. You're going to learn today. I have never heard the word deadheading until today. Most of you know me, but if you don't, I'm Danielle McLean. I'm the founder and CEO of HYSKY Society. So I am thrilled to be here with you today. So what is HYSKY Society? HYSKY is a 501c3 nonprofit committed to decarbonizing aviation and aerospace with hydrogen. We welcome and unite innovators in eVTOLs, fixed-wing aircraft, lighter than air, wing and ground vessels, drones, UAVs, and spacecraft. If it flies on hydrogen, it's part of our vision for sustainable flight. Our mission is decarbonizing flight with hydrogen by building a connected ecosystem. Ecosystem is highlighted in purple because I want you to pay special attention to that word because that is you. Our vision is zero carbon flight powered by the hydrogen value chain ecosystem, which is you. We're going to talk more about that. And if you saw my note on the surprise today, it has to do with that ecosystem. So HYSKY programs, I'm not going to read this whole slide. I'm just going to read the highlights and then you can look at them later. But we have 6 programs. HYSKY Monthly, Flying High, which shout out to the Flying High Steering Committee. Flying High is our in-person, which is virtual this year, but it's usually our annual in-person aviation conference. And we just launched our steering committee. So huge shout out to everybody that is on the steering committee. You all are doing an excellent job. And I'm so happy that you all are with us. We also have HYSKY EDU, where we do courses. So far, we have one with AIAA, but we're getting ready to launch more. We have our H2 Hub Summit, which we just did in March. That is also an annual event that focuses on hydrogen production. We have HYSKY Pod, which is our HYSKY podcast. We've had Dean Kamen, the inventor of the Segway, on there. Martine Rothblatt, CEO of CEO of United Therapeutics, and also Mikhail Cardinal, CEO and president, not CEO, I'm a hot mess today, president of Unither Bioelectronics. And our 6th program, HYSKY Connect, which we are announcing today for the first time. So you all have seen me show this slide for years, and I have talked about this forever, I think for at least 3 years. But the hydrogen aviation ecosystem is critical to exist if we want to fly with hydrogen. A lot of times, especially those of us like me that came out of aviation and aerospace, we often focus on this part of the ecosystem, which is onboard storage, fuel cells, and the aircraft itself. We don't often think about infrastructure and refueling, the logistics of hydrogen, and the hydrogen production. But it's critical that we have all of these pieces. Some of us have learned the hard way that even though hydrogen is the most abundant molecule in the universe, You can't buy it at Walmart. You can't order it on Amazon, and it can be quite expensive, especially if you want green hydrogen. So that's really why HYSKY exists. I'm going to kind of jump around in here, but HYSKY exists to bridge the gap between hydrogen and aviation. So for those of you that have been with us for a few months, we've been telling you to complete this form to join the hydrogen aviation ecosystem. And I am going to put the link again in the chat. And go ahead, if you're interested in being listed in our database, then go ahead and join or just complete that form. And let me show you what that actually looks like now. So before, it was just a form that you completed. Well, we've officially launched HYSKY Connect. HYSKY Connect is where hydrogen meets aviation. We're connecting hydrogen and aviation to enable zero carbon flight. So I am so excited to announce HYSKY Connect to you all today. This is an ecosystem where you all can chat with each other. So if you're doing hydrogen production, hydrogen logistics and delivery, refueling and infrastructure, onboard hydrogen storage, fuel cell development, aircraft design, any of those things, then you are part of HYSKY Connect. And right now, I believe it's open to everybody, but don't worry, if you complete the form that I stuck in the chat, you're going to get an invite and you can join for free. And so once you join, you'll kind of see what that looks like, but why we exist. And I'm not talking about we HYSKY, I'm talking about HYSKY Connect. Hydrogen and aviation are advancing, but often separately. Most hydrogen producers and logistics providers aren't thinking about flight. Most aviation teams exploring hydrogen have no clear path to sourcing it or finding the right partners. Zero carbon flight cannot happen in silos. That's why HYSKY Connect exists. We connect hydrogen producers, logistics providers, infrastructure developers, onboard storage experts, fuel cell innovators, and aircraft builders and developers. We create the relationships that turn technology into flight. HYSKY Connect is the bridge between two industries that need each other and now have a place to meet. So what you get with membership, you get your company listed in the HYSKY Connect database, direct messaging and access to other members, complimentary initial consultation with Carter DeLuca. I'm not going to go through all of these, but like I said, complete the form that is in the link that I stuck in the chat, and you will get an invite to join HYSKY Connect. So what is HYSKY Monthly? HYSKY Monthly is what you're at right now. It's a series of free educational hydrogen webinars. We host them on the third Monday of every month, and they're for anyone interested in hydrogen flight. We have hundreds of hours. We're probably close to thousands, at least 8,000, hundreds of hours of expert hydrogen aviation videos free on YouTube. So I encourage you all to subscribe to our YouTube channel if you haven't. I've just put the link there. That is also a way that you can really help get the word out and help our algorithm. So all of our podcasts are also on there. So if you're interested in hearing more, I encourage you definitely go watch the interview I just did with Mikhail Cardinal. As many of you know, Unither Bioelectronics just flew the first ever hydrogen-powered helicopter, and we have exclusive video footage on that podcast that is not anywhere else. And I interview Mikhail for over an hour, and he breaks down all sorts of cool stuff on that episode. So definitely go watch that. And you can find that by subscribing to our YouTube channel. So now just quickly, I like to do this part of this presentation because we have a mix of people. We have people that are from hydrogen and we have people from aviation. So this is kind of, my way of bringing it all together. So why hydrogen? I like to use the use case advanced air mobility with batteries, but this could also be with drones or fixed wing aviation or commercial aviation. So whatever form of aviation you're comfortable with, you can use that. My favorite is just advanced air mobility. If you don't know what that is, look it up. We also have tons of stuff on our website about advanced air mobility. So also, if you don't know the term eVTOLs, it stands for electric vertical takeoff and landing. So that just means that you can take off vertically like a helicopter, but you're electric. So battery powered eVTOLs are great. They can fly over traffic. That's good. They can go about 60 to 100 miles. That's okay. This Beta aircraft over here can actually go 250 miles on batteries. That's because it's got wings. So the cruise is much more efficient. But if you wanted to fly from Houston to San Antonio, say on like an electric helicopter or another eVTOL, you would have to stop and charge. And for me, that's bad. That takes a long time. We don't want to have to do that. And this is just a funny AI generated photo of Elon Musk judgingly looking at the Beta charging, the Beta Elia. No shade to the Beta Elia aircraft. It's a fabulous aircraft and we love Beta. It was just the only, this is not AI generated. It was the only actual image I could find of an electric aircraft charging. So the key takeaway is if you want to go from Dallas to Austin to San Antonio, and I'm speaking because I'm in Houston, you have to stop and recharge. And we don't want to do that. We want to go straight there. Hydrogen can extend the range a lot. It can extend the range to 300 plus miles. And Mikkel and I talk about on that interview, it can actually extend it, the Beta Elia, to 750 miles and then some. So this opens up city to city travel, state to state travel, life-saving flights that average over 300 miles, regional air mobility, emergency search and rescue, think floods and hurricanes. Of course, I'm in Houston, so that's at the forefront of my mind. But this basically enables zero carbon flight pretty much anywhere. And this is just a graphic that shows what's capable with hydrogen versus just batteries. So if you wanted to go 300 miles on batteries alone, you would have to stop and charge twice. If you wanted to go 300 miles with batteries, you can go from A to B in one shot. Or you could go 150 miles with no infrastructure on the other end and then have enough power energy to come back to point A. So hydrogen just really opens up the range and the capabilities of what you can do. Of course, this a short little video of my in my imagination, this is what I want to do. I want to go to all of these locations without having to stop and recharge. This is a slide that I really need to update, but I think it's about 6 months old. But these are, as of 6 months ago or 8 months ago, all of the companies that I found that were working on or had flown with hydrogen. There are at least 5 that I need to add to this. Beyond Aero. Oh, I do have Beyond Aero on there, but there are some. I saw a great graphic on LinkedIn about 3 weeks ago that had some companies that I was like, oh yeah, I forgot they're doing hydrogen. But the point is, these folks are already flying with hydrogen or are looking at flying with hydrogen, and they're going to need hydrogen, but they're not in the business of building hydrogen infrastructure or hydrogen production. So HYSKY bridges the gap between hydrogen and aviation. You know, we don't source it ourselves, but we look for companies that are producing hydrogen. We look for companies that are selling power and doing PPAs for hydrogen production so that people that need to fly with hydrogen have the hydrogen that they need, where they need it, when they need it. This is just a quick announcement. I think this is an old slide, but I'll go ahead and talk to it. Flying High 2025 will be virtual. And just because of federal travel restrictions, budget cuts, and making it easier for everyone to join, made it the smartest choice. And so I'll go ahead. Tickets are on sale now. I will go ahead and stick the link in here. Because it's virtual, it's actually on our homepage. So you can just go to our homepage. Because it's virtual, tickets are $30. I would encourage you to join. Usually we charge like $800 to $1,200 for this event. So definitely go in. We also launched a steering committee. I talked about that earlier, and we did a survey on what people wanted with Flying High. We've published the survey results, but it's not going to let me copy the link. So you can read that. It's actually really interesting. We had like, I think 80 people complete this survey. So it's a really cool survey that just kind of showed like what you all want to see. Okay, now my favorite part of HYSKY Monthly is I'm going to stop screen sharing, and we are all going to turn on our camera and take a group photo. And I will post this on LinkedIn. And then just give me a minute to, I don't know why I struggle on this so much. Okay, we'll give everybody a minute to turn on your camera. And I'll tell you before I'm going to take the picture. I'm still waiting for the screen to fill up. It doesn't matter if you're in your PJs and working from home or have kids in the background or pets. We don't mind. Okay, awesome. Everybody say hydrogen.
Hydrogen.
Awesome. And let me do one more because I usually mess a couple of them up. One, two, three, hydrogen. Amazing. Okay, gonna go back to sharing my screen. Thank you all. I love those pictures. When they go on LinkedIn, they really make everything feel real. Sorry, I'm sharing the wrong thing. I see. Bear with me. All right. Okay, hopefully you can see that again. These are some pictures from previous HYSKY monthlies. It just makes it feel so much more real when we get to see everybody joining. All right, finally, without further ado, meet today's speaker. Oh, I am so sorry. This definitely should say Philip Stuckey, Dr. Philip Stuckey. I forgot to update that part of the slide. Forgive me, Philip. Dr. Philip Stuckey is founder and CEO of FC Renew. He's focused on research, development, and commercialization of extended life hydrogen fuel cells and recovery of precious metals and critical materials for hydrogen fuel cells and electrolyzers. Dr. Stuckey has over 22 years of proton exchange membrane, PEM, fuel cell experience directly related to research, development, and intellectual property. With FC Renew, Dr. Stuckey is principal investigator for Small Business Innovative Research (SBIR) awards from the National Science Foundation (NSF), U.S. Department of Energy (DOE), and U.S. Army. FC Renew has expanded its service to include the purchase of end-of-life hydrogen fuel cells and electrolyzers for domestic responsible recycling of critical materials. FC Renew's holistic electrode approach reflects their dedication to commercialization within the fuel cell industry. And without further ado, please welcome Dr. Philip Stuckey. Dr. Stuckey, the stage is all yours, and everybody else can go ahead and mute and turn your camera off. And go ahead and take it away.
Thank you, Danielle. Yeah, it's great to talk to everyone here today, and I'm really excited to be here, have this audience. So I up front want to say this to me will be an interactive presentation. I have no problems with questions at any point through all this. This is about as long as I've ever gotten a stage for in this kind of setting. So please do ask questions. But I'm a fuel cell person by background, over 20 something years now directly related to R&D on those efforts. And I think it'll come out pretty clearly on these slides. But before I go ahead and start screen sharing everything, I just want to say that this application for hydrogen aviation has a true route, and I think it's a true good win for hydrogen fuel cells because of the system and the power density that hydrogen fuel cells can deliver over to there. So I wanted to, just go ahead and kick that off. And in terms of my talk today and discussion, the whole idea of recycling precious metals is absolutely critical to the success of this whole technology, because the platinum that drives the reactions in hydrogen fuel cells that becomes the powertrain for these applications is an expensive material. It's mined not domestically in the United States, not in Europe. So these are all areas and markets where the technology is trying to enter into, but needs to be really careful. And my pun not being the aviation people that everyone else in this room is, deadheading of platinum was kind of my thought, thinking about flight attendants having to travel to different places and things like that. The whole logistics of getting people where they need to be to make the whole aviation and commercial aviation work. Platinum kind of has that same route. You have to get it from the mine into the hydrogen fuel cell, and then what happens to it afterwards. So with that in mind, the whole concept here is, let's talk about platinum. Let's talk about what we're doing with platinum. And I think everyone can hopefully see my screen here now.
Yep, looks great.
All right, thanks, Danielle. So yeah, I'll go ahead and kick it off. So the whole concept here today is that we're going to talk about recycled precious metals for fuel cells. I put a LinkedIn QR code up here. Please feel free to, drop me a message on LinkedIn, reach out to me by email. That's my cell phone number there. So feel free to reach out at any point to continue this conversation. But I just want to say we're an R&D group. So we're about 5 years now into FC Renew. And we have a wet lab that is leased at University of Tennessee, and we're deep tech R&D. So we've had a lot of opportunity to be able to showcase our technology, but we also have access to a lot of resources that I think are pretty unique, one for a startup company and two for companies in this type of industry. And we have a team of experts. So I myself have over 22 years of experience in this industry. I've been interested and an enthusiast of hydrogen, from early on in my undergraduate career through postdoctoral studies. I spent 8 years examining fuel cells and batteries at the USPTO. And then I got into Innovation Crossroads, embedded for 2 years at Oak Ridge National Laboratory, which really gave us the ability to kind of kick this off. And some of my other team members are here with us today, but we have Jamie, David, have strong backgrounds in electrochemistry and fuel cells as well. Both of them have great working knowledge of membranes and the polymers inside of this. And we all share this kind of electric catalysis mindset. And Tyler, who's joined us today too, as I talk about some of this work, we have a real team effort here. So keep in mind that I think some of the companies that are used to being here are quite a different perspective and landscape than where we are. So without further ado, I'll kind of get into it. I know a lot of people talk about Toyota Mirai stacks, but here's a Toyota Mirai stack on a pallet that we had sent to us from California. And on the right-hand side is all of these materials here. And before we really kick into the direct precious metal recovery, it's been suggested that I kind of go over some operations of fuel cell and why platinum is so important in hydrogen fuel cells. So as I get to that, we have our core processes for recycling and for this renewal process. And I'm just going to go ahead and skip forward to this graphic here, talk about fuel cell operation. We'll talk about this again, ask questions anytime. And then from there, we'll move forward. But basically, a fuel cell at the end of the day has two components, an anode and a cathode. And this is what the hydrogen fuel cell inside a Toyota Mirai stack is and what it looks like. So as what you see there in the graphic on the screen is hydrogen from the anode side reacting at a platinum catalyst. It breaks in H2 breaks into a proton, H plus, and on the other side, oxygen from air enters. O2 breaks into O negative on the surface, and you can see the reactions on the screen here, but H2 plus O2 yield water. And this has the electrochemical potential to drive that reaction. The electrons go through the external circuit, but all these reactions occur on the surface of platinum electrocatalyst. And so you have to have that platinum available inside the system for these to occur. So as we talk about this and talk about the industry, what's changed? Because platinum itself has not changed in the last 20 years or so, but there have been a lot of, good improvements in hydrogen fuel cell and stack technology. And the MRO, again, I'm going to kind of single that one out there. But if we look at Gen 1 to Gen 2 and Gen 3's coming out, earlier on, you had 200 cells, you would use 2 stacks, 400 cells, and engineering improvements have really gone into making these stacks something better. So what I'm actually going to do is stop sharing for just a minute and bring back up my screen, and hopefully this is helpful to everyone, but this is the inside of the Toyota Mirai stack, right? So in the last 20 years or so, why this is important for power generation is you have all these different flow fields, you have all these different components that have to deliver hydrogen and air to here, remove the water, keep this unit cool enough that it can operate. And then they package these together, and these are really slick. And then you put 370 of these inside a stack, and they deliver gas flows and everything else. But it's all been mechanical and kind of engineering choice design changes over the years, in my opinion, because all these little channels affect the way that hydrogen and air get to the electrode and the way that the water is expelled from the cell. So all these little pins, all these little things basically have that mass transport effect on the way all these gases are moving. So these are incredible engineering feats that have, effectively cut in half the weight, double the power output, but at the end of the day, it is still platinum that is driving and at the center of all these reactions. And that still has not yet fundamentally changed, because those reactions that I just showed, they are really at the heart of all this. So I'm going to get back to this presentation here with that and kind of talking about why in a little bit that's a problem. Because if we look at stack lifetime, and I know that's not exactly the first big problem for the aviation and hydrogen, but if we look at stack lifetime, and 5,000 hours is a little low, it is higher than that. But you have a very high power demand application here. And so if we talk about how many fuel cell stacks you're going to need in something for eVTOL, we're looking at least 2 or 3 complete replacement of these stacks over time. That adds up in costs, that adds up in maintenance costs, that adds up in catalyst costs. So I've got also kind of a cutaway from BMW from a while ago. You can kind of see all the differences and technologies that go along towards getting to where we are today. So let's bring it back here to like what's happening inside that fuel cell. Every time you take off, you're going to do things that destroy the catalyst. So you wind up removing platinum from the surface, and this is kind of a schematic where this would be on carbon. But if you imagine these as platinum particles, every time you polarize and want to take off, platinum comes off the surface. These particles, they can ripen together, or they can agglomerate. And as what happens is you wind up with this surface area reduction. And why that's a problem, because all those reactions I just talked about, they occur on the surface of the platinum. So if you imagine a beach ball and a bunch of tennis balls, a bunch of tennis balls that fit inside a beach ball have way more surface area than that one beach ball. And because you want surface area to drive your reactions, over time, all these mechanisms during operation lead to, less performance because you wind up with less surface area. And so this is what starts to drive fuel cell lifetime, is the actual movement and the actual stresses that the catalyst undergoes during all these operations. And to put this a little bit more into kind of operational terms, a fuel cell at open circuit voltage, when you have no load on it, just sitting there, not drawing any power, will be at about 1 volt. And as you start to polarize this and draw power, you bring it down to like 0.6 volts on this one individual cell, maybe not much lower, but somewhat lower than that. So all the platinum inside there undergoes a surface change that's directly related to forming hydroxide. And there are a few, I think, different theories on what this actually is, and I think some relevant discussion on that, but we'll call it PTOH for today. And this PTOH forming, you can see the way the surface would form. And then when you go back to open circuit, it gets released from this surface. So this is, the actual stress and the surface changes occurring. So there's also a lot done with the whole overall balance of plant to try to make sure that you're not overstressing those conditions during operation. So there's a lot going on here. And then just to back up too, talking about these gas diffusion layers in terms of just some of the engineering that has to go into these stacks. This is some of my old work from graduate school, but kind of relevant here. These gas diffusion layers have a lot of roles too, where they have to push the water into the cell, but also make sure it can come out. Because if you're flooded with water after you've produced it in the cell, you can't actually diffuse the gases back to the electrode. And that's a huge problem in the cell too. So there has to be engineering along all these different components of that. So before I continue on with kind of FC Renew's processes, I'll just stop and ask if there's any questions.
Don't be shy. If you have a question, you can type it in the chat, or you can turn your camera and mic on and ask.
All right, Danielle, and I'm having a hard time transitioning to the chat and back and forth. So if there's anything there, just let me know. But what I'm going to do now is kind of talk about recycling, because this is what we came here to talk about today. So our core process to recycle is to get the platinum back out of these stacks. So if we think about kind of what happens during the stack, you put a new stack in a vehicle, you put it in a plane, over time that's going to degrade. And once it's degraded, you can basically take it through this first loop through the recycling process. And we've done a lot of work towards extending the lifetime of hydrogen fuel cells, which I'll talk about a little bit later. But that would be to reuse the fuel cell in its application without having to fully replace it. But at the end of the day, recycling and end of life, you want to collect these precious metals. And part of the reason why I show this stack torn apart is because this is a lot of what conventional recycling processes are. If you were to take this whole assembly and just simply try and recycle it, the amount of platinum in it's really relatively small, and you'll have a hard time getting it directly out. So is what somebody really needs to do right now is take these things apart, that whole stack apart, get this MEA out, and then these MEAs effectively go into a 55-gallon trash can, and then they get sent off for pyrolysis and for recycling. Is what we do is a direct method to extract from assembled hydrogen fuel cell stacks all these precious metals, the platinum, the iridium, from electrolyzers, ruthenium, if that's a different type of catalyst system that might be used, or cobalt if you have like a platinum alloy. And so we actually will pay for old stacks in a tolling and cash model. And I'll go towards renewal later on. But I also want to talk about kind of some of the processes that we do too, because there's a lot of literature out there, and then there's actually doing things in real fuel cell stacks, and they change from time to time. So with kind of the I'm sorry for jumping around there. The really ex situ methods are very small, fine electrochemistry, very controlled environments. But when you actually get towards the stack side of things, the whole components change and it becomes a systems level approach. So we can, at FC Renew, we have the background to do both. And so we're working between theory and the actual stack operation to achieve our goals here. So now I'm just going to skip ahead back to recycling and why ours is different. So we're not pyrolytic. So if we look at all the other pyrolysis processes, and pyrolysis just means burning, we don't burn these. So right now, in order to collect the precious metals, this gets burned at a high temperature so that basically all the carbon burns off, all the Nafion or PFSA that's inside of this gets burned off. When you burn that, that releases HF gas, but what's left is effectively ash and then the platinum, because the platinum burns at a higher temperature. So then that would be collected, it would be assayed, and if you had a bunch of fuel cell stacks, that would be assayed, and then you would be given an option more or less with some of the traditional recyclers to either receive back some various grade of platinum metal or a check. And effectively, as you could imagine, if you take the cash out, you're going to get the least amount of money back. If you take back platinum metal, then you kind of have to start to discuss, well, what grade are you going to take? Do you want that ash, or do you want something that is in a solution, or do you want 99.99% pure metal that you could hand over to a catalyst supplier? These are all aspects to consider in the market. We're entirely different in that. We still can operate on that approach to work with you on that, but we have a different process. So while they have to do all this burning and things like that, we can extract them straight from the stack. Our process doesn't require stack disassembly, so it's a little bit different in that regard. So I believe as we continue forward, we can actually get higher margins for platinum materials in the current processes. And then this is a service to a lot of other people, because you all here in this room want to be focused on getting aircraft from point A to point B effectively and efficiently, and you don't want to be thinking or worrying about your end of life. So this relieves that from the end of life and the burden from all you people who are trying to get these systems going. And in terms of security, precious metals stay more local. They remain within borders. And when we think about that in terms of supply chains in the United States, I think, you know, we're largely populated in this group by that. The precious metals remain within our borders, and that can help, you know, continue the loop in the supply chain. And because we're less energy intense than pyrolysis, we have a different aspect there. But thinking about our process too, we're actually also able to capture this PFAS. So if we think about future bans that are most likely to go in place in Europe, this is certainly of a consideration for that materials issue. And I'm just going to jump now straight to some of our results that are public with our Department of Energy funded work. But we were doing some of this testing on just kind of lab scale MEAs because it was an early project. And this data is now well over a year old. And we do have better and more data from systems. But effectively, you can see what an unprocessed membrane electrode looks like without the black gas diffusion layer over it. So it's platinum on this side, platinum on the other side, and then it's framed with the Nafion membrane. And one over here is one that we processed by putting it into an actual hydrogen fuel cell housing, doing our process, and then taking it back apart to show that. So is what I have here is basically the requirements that DOE put out there as targets, which are good targets. So reduction of hazardous substances basically means that if you're not burning, you're not releasing all this PFSA and HF. So we were able to do that because our process is inherently different. And then as what I'm showing here is, again, a year old, but this is a transmission electron microscopy of the catalyst support. So the platinum is all the white dots, and then the platinum supported on the carbon to actually be inside of that electrode. And our process is able to directly remove the platinum from the surface of this and flush it straight out of the system. And we consistently get yields in the 80% of recovery. And we're very close to the traditional pyrolysis methods there, but which are in the high 90s. But the key difference here is we have way fewer process steps. So our process is much less cost intensive and energy intensive than the other. So we actually have a competitive process for the status quo. And I'm going to kind of turn it back around, but we've developed a whole custom system, and this is what some of our dashboards look like, because in addition to just extracting the metal from the hydrogen fuel cell electrodes, we want to understand the rates, what it does to operation, how we can improve upon our process. So in addition to being able to do just our process, we've built these whole custom systems that can actually operate hydrogen fuel cells and capture all relevant data in real time from research grade potentiostats, which show us things like the open circuit voltage of the fuel cell, which is that where it's at rest. We get high frequency resistance of the cell, which gives us insights as to both membrane health and how much resistance is in the cell and what our process has done to that there. And then we can actually operate the hydrogen fuel cell by supplying hydrogen and air to it, and we can measure the power output of that so that we can have an understanding of that. And then we can rinse and repeat and watch the change in electrochemical surface area change over time of the fuel cell electrode. And so kind of putting all that into higher play from kind of our scientific-based approach to developing this industrial process, we've built different systems, different architectures. We've looked at a lot of different components. So single cells, different configurations, short stacks, the types of hardware you see here. We've looked at flow fields, but again, we'd be looking at taking something directly out of these fuel cell stacks. But we're able to do all this custom testing as well, which I think extends beyond just recycling. So we can flow in various gases, we can monitor things in real time. And our team's built things where this type of data gets processed and analyzed in real time through scripts. So someone's not actually having to go through. And when we want to get electrochemical active surface area, if that means something to anybody in this room, we've written scripts and computer programs that directly do all these calculations. They get binned up in reports and they get directly outputted to us for us to view, as opposed to having to try and do all this data processing manually. So when we talk about recycling, this is what we're looking at. If you want to deal with taking apart something like this to get it to your metals recycler, you're welcome to do that. But we kind of are taking a different approach of why we think that's relevant here. So I will pause again for questions, but I think I'd actually rather go talk a little bit about some of the market and why aviation has some relevance here before I go on.
Thanks so much, Dr. Stuckey. We have a couple questions. If you want to keep going, you can, but it might be helpful for the audience to follow.
Sure.
I'm going to call on Sarah. Sarah, you're definitely, I think we need to make an award for our most active participant. You always have fantastic questions. If you want to unmute, tell Dr. Stuckey where you're from, who you're with, and you can ask your questions.
Appreciate it. Sarah Mitran, I'm with Nath Management Consulting. I support SBIR grant recipients and help companies with their commercialization. So for context, I wanted to know how much does it cost to do this type of extraction, and obviously how much water is needed, whether there are any health risks for the, for folks that are working in this process, and how much demand is there for recycled materials. And I always think of recycled from the context of plastics, right? Once the plastic is recycled, it has there's less interest, so has to be like a specific market for it. So hope that helps.
Yeah, we can talk about all those too, because you're absolutely right on so many of those things. How much does our process cost? It's very inexpensive. We're talking about hundreds of dollars in materials that we use to extract the platinum from a stack. So we're looking at, maybe 20 to 100 grams of platinum for effectively that much in terms of raw materials. And in terms of health to the workers and the people around it, that's been an effective design case from the beginning. Not in small part because, we're doing the work ourselves, but also because in terms of making this process commercially viable, you want to be able to do that. So we've taken into account the types of materials we're using. So I will say we don't use something like hydrofluoric acid, just because that doesn't really play into that vision of making these processes effective. So I'm actually sitting in our R&D lab right now, and everything we do in here, and I'll just kind of turn around and show there, we've got our fume hood over there. We've got our testing equipment right over here that we
Hi.
built.
I saw somebody wave, so I just wanted to say hi.
Yeah. Yeah, nice. So we've got all the testing equipment here. So in terms of the health risk, this would go into a traditional warehouse type setting with a few special outfits without having to be anything much larger than that. And I really like the question. And did I hit most of that before I go into the demand for recycled material?
Yes, I think so. Thank you.
Awesome. Well,
And
great.
real quick, Dr. Stuckey, John is asking what is MEA? I also don't know what that is.
All right, good. Membrane electrode assembly. So at the heart of that hydrogen fuel cell, and we'll skip back to that graphic really quick here, actually, if you want. I don't need to. This is a membrane electrode assembly. So at the heart of it, membrane and then two electrodes, anode, cathode. And so the membrane in the middle has a function of being a proton conductor. So that's what separates the two electrodes electronically, because it's electrically insulating. And then the electrodes have an electric property as well. And I think, it's a really good question. So let's bump back up to the graphic in the beginning and kind of go through that one more time. And so at the heart of the fuel cell is the membrane electrode assembly. And you have electrode, membrane, electrode. So that is it. And again, there's got to be properties of this because you have to have the electrons be able to drive through the external circuit. So all the material on one side of the membrane and the other side of the membrane have to have an electronic conducting pathway. And if you ever hear of people talk about three-phase contact, is what that is solid, liquid, and gas. So you have the membrane, which is considered liquid because it's a polymer electrolyte. So think electrolyte in more traditional terms. That's your liquid. Your solid's the catalyst, platinum. And then the gas phase is your reactants, the hydrogen and oxygen. So you have to be able to diffuse the hydrogen directly to the surface of the metal where it reacts on that surface. Then the electron has to be able to come externally back through the fuel cell itself, through the housing, and that's connected up to your motor effectively. So the electron's coming out. And then you also have to have the proton going through the membrane to meet up on the other side of the electrode to be able to produce the water. So that's the overall reaction mechanism. So both these sides also have to have that. And keep in mind on the cathode, you're producing water. So as you go through that reaction, if you flood this with water, that oxygen can't diffuse to that surface. So that then becomes effectively stopping the entire reaction. And then you're not going to be able to produce power for your system. So that's been taken care of a lot with all these designs, so that you ensure that you have a system that can operate under different conditions, drawing different amounts of power as it's needed for the drive profile or the flight profile. Yeah, and any more questions on that front? Happy to go through those at any point there too.
This might be a dumb question, but I don't know. They always say there's no such thing as a bad question.
No.
I think, and I guess, how do we typically source platinum? And why do we need platinum from to a 10-year-old? That would be helpful, I think, to our audience.
Yeah.
We hear a lot about rare earth metals, but from, folks that are typically looking at on board the aircraft, in our group particularly, we're not usually the ones developing the fuel cells. We're working with folks that are. So yeah, I'm so happy you have this. Like what is involved in sourcing platinum, and why is it so innovative and important what you all are doing?
Yeah, so this just kind of came through my email a week or so ago, but where is platinum coming from? Platinum typically is found about 95% with iridium in ore, and it's mined. And most of the world's supply of platinum comes from Africa right now, which makes it a little bit different than some of the critical materials we think about in the battery industry. So it gets mined, it gets processed and refined, and then it gets shipped out. The largest companies that dominate this, like the Johnson Matthey's, the Heraeus, the Umicore, they're global companies. They operate in like 140 plus countries, and they really do have, from the mine to the material being processed to the material being sold, and they also have back-end markets for all the recycling, very well established type of material supply. So that is what's going on there. So I think that answers that question. And then going back to some of the supply here too, there are already recycling partnerships in the industry. So Plug Power, being a major US hydrogen fuel cell producer, has a relationship with Johnson Matthey to go ahead and recycle these. And I'm less familiar with their precise recycling processes at this point. But as what I can kind of say in terms of the market right now is really small. Hydrogen fuel cells tend to be in a demonstration mode. So if we look at kind of recycling, and in terms of how that works, there's about a 10-year offset from the day something goes into service to the day it's available for recycling. Because if you look at right now where we are at 2025, we're looking backwards in time for all the things that are ready for recycling today. So don't discount for recycling, some of these demonstration projects in aviation as well, because the fuel cell system in a forklift is relatively small, on the order of 100 kilowatts. But if you're talking, 600 600 kilowatts plus for some of these aviation systems, there's a lot more platinum in them, because you have to have that amount of surface area and that much platinum to generate the power. It's all directly proportional. So I put these kinds of numbers on these graphs here to talk about the market size and how it grows over the years with the deployments. And at some point, marine rail, and that's where aviation should be coming into play, should start to dominate, as well as heavy duty markets, because with fewer number of systems put in place, the amount of metals increase that much more. So while there's 40,000 plus forklifts in operation in the United States right now, there's only a handful of hydrogen powered, eVTOLs or planes. So that is to be considered. And
Dr.
also,
Stuckey?
yeah, go ahead.
Yeah, question real quick.
Yeah.
A question about the function of iridium in a fuel cell as distinct from platinum. You've explained platinum as the catalyst. What does iridium do?
Yeah, so iridium's on the other side of that, and that is been into the electrolyzer side, which is another area that we are beginning to work on. We have the hydrogen fuel cell side mostly behind us. But if you look at the electrolysis options that exist, the traditional alkaline don't use the iridium or platinum catalyst. But if you look at PEM electrolysis, which is using a very similar type of proton exchange membrane, PEM electrolysis is the newer version that's associated with green hydrogen production. And those electrolyzers use platinum and iridium in the electrodes. And they're important for a couple reasons in my mind for this industry, because one, if you want to be able to ramp up and down production of hydrogen, alkaline electrolyzers can't go from 5% to 95% power intake and hydrogen output quickly. They don't really scale that way, whereas PEM electrolyzers do. PEM electrolyzers also produce that high purity hydrogen that would be needed for proton exchange PEM fuel cells. So that's where the iridium comes into play here, and why I think it's kind of a twofold market for the precious metal side there. So yeah, and that's why that comes into play here, because both these are going to get deployed, you know, relatively close to each other, and electrolyzer life expectancies are a bit longer than the fuel cell stack expectancies from the way they're sized and designed. But still, at some point, iridium's 6 times more expensive than platinum, and iridium's a bit more scarce than platinum too. Not that either one is necessarily abundant, but I think both of these metals are going to be things to watch over time as we look at that. And so kind of taking this backwards and looking back at our deployments to where we are today, one of our other opportunities was through Energy Works and Strategic Analysis, funded by Department of Energy. And they actually took our process and modeled it out and looked at our market size as well. And this is kind of where we were able to come up with. And this is not the best market size to go show an investor for venture capital. But this is also why I'm excited to be here with this group today, because we are kind of at a demonstration phase with some of these things too. So the ask for me here to you all is to work with us in recycling your systems that you have. And I think too, for this hydrogen fuel cell deployment or electrolyzer deployment in this space, you're going to have systems that you're maybe going to fly a handful of times and say, that's it, because, you know, there's a risk to flying unknown systems a certain number of times. So I think there is kind of an opportunity to get around what you can see for the actual commercial deployment versus what is needed for the demonstration phase. And don't discount if you have a warehouse or, you know, a room with a bunch of fuel cell stacks in it from previous work, we would be happy to work with you to get those disposed of and get the precious metals reclaimed and go ahead and kick off this component of the supply chain. And so I put that there.
Another thing I just want to add to this conversation. Apologies for interrupting, but I'm having a thought. So in aviation, we call it MRO, maintenance, repair, and overhaul. That's an important piece to getting a new system certified. So a new propulsion system, we need to know what the life cycle is, what that looks like. And so, you know, the hydrogen fuel cell powered aircraft are not certified yet, but having this as part of the conversation, I think is really important. So I could also see there being opportunity with you all working with the FAA and some of these organizations, because you have to have an oil change on a typical aircraft. So and as you know, when we were
Yeah.
talking, you mentioned this is kind of like an oil change for a fuel cell. So I think this is a really important piece that the FAA would want to be educated on.
That's an excellent point, an excellent suggestion. And I will take any of those because I don't fully understand, how your side of of this whole systems and processes work. So with that in mind and kind of going on from there, these are really more or less kind of the key points here in terms of thinking about end of life and recycling. These stacks at end of life need a specialized attention. They need some labor and they need proper disposal to get the value back out of them. And the recyclers today don't want assembled stacks. They want to get as close to the precious metals as they can to get them back out there. So we can take process stacks owned by individual customers or in partnership with a larger supply. And then another kind of thing, people's internal designs, I think you might notice this too, people can get very protective about what the inside of this looks like. So we can work with NDAs and other confidentiality and ensure complete destruction of this to help protect intellectual property. So that's our offering. And I will also say the number of units that we can work with you on is not too small. So if you have just a couple or, one, that is enough to start right now, because as we talked about the supply chain in this, the market's small right now. And I think too, we have a small overhead for our business. So we're actually really well situated right now, I think, to grow with this industry. And as we talk about an oil change for your fuel cell, I'm going to bring up the renewal process that we're developing, because this is not recycling. This is what's happening inside the electrode. So over time, we talked about all these mechanisms that cause the hydrogen fuel cell to degrade, and after several thousand hours is what you go from is having these nice decorated, these would be platinum particles on the carbon surface inside a cross section of that membrane electrode assembly. And as you operate, I'm sorry, I'm moving my mouse, and as you operate, those particles start to ripen and you lose your surface area in your reactive site. So renewal, and how we call this an oil change for your fuel cell, is that we're doing processes whereby we do an injection of material and we do some other type of applications to the fuel cell stack to cause that platinum to redistribute in the fuel cell stack. That way you can get back to this distribution that looks more homogeneous with a greater number of sites that are reactive inside the process. And looking at some of the data, just kind of one snippet, and this is transmission electron microscopy with a high mag, so very zoomed in on just very thin catalyst layer right here. So what we're able to do is show we can move the platinum. So we've actually concentrated it. This micrograph is a heat map. So the red spots show a lot of platinum, whereas all the blues basically show platinum, but a very, very low amount of platinum. And we can move it towards the membrane and the electrode. We can recycle it by moving it out. So we have control, and you don't really think about the catalyst as being mobile inside of a hydrogen fuel cell, but we develop processes where we can move this in 27 minutes. So we're on our way to doing this lifetime extension or an oil change for your fuel cell. It's certainly more R&D right now than it is a commercially available technology. Whereas recycling, we can do that right now, and the market's really small. So these are kind of our two core technologies where we founded FC Renew and excited to partner on both of them. But again, we need to work on all these items here as well. And I'm going to show some really detailed data here because don't often have the chance to do that. But the commercial impact of this is high. And as what we can show here is that effectively we can affect the surface area of the platinum in the electrode and cause it to increase with some of our processes. And we can do accelerated stress testing in our laboratory too to further degrade that catalyst inside of there. And we're working on doing recovery processes to actually bring back to life the performance of fuel cell stacks. So instead of being as concerned about recycling them, you can think about this, as you say, with the FAA, the tune-up, the oil change, doing something to ensure that that fuel cell stack that's mounted and integrated into the plane, the wing, the fuselage, wherever it's going to be, has something that can be done to it to bring thousands hours more a lifetime to it. Yeah. So, you know, with that, I'm going to back up a little bit and ask for some more questions.
I just want to make a comment really quick. I didn't do housekeeping at the beginning, but I would like to encourage everyone to ask your questions in a very respectful way. We're very lucky and grateful to have you sharing your time. So with that said, I would ask you, could you compare, I don't even know if I'm going to say this right. I hope I don't butcher it. We're getting into the weeds of way out of my expertise. But could you compare using platinum with graphene and borographene and why you guys are choosing platinum versus boron doped graphene?
So I'm not familiar with the boron doped graphene as a catalyst as compared to platinum. But there's a whole field of different catalysis and catalyst studies. So platinum is the gold standard, so to speak. It just works. In terms of the hydrogen reaction that's occurring there, it is the definition of an ideal electrode, meaning that there's really no kinetic loss. Hydrogen will break apart into protons on platinum with almost no efficiency loss. It's the other reaction, the oxygen reduction reaction, where platinum is the best known material for driving that reaction. And if you want to start to look at using other catalysts inside of a PEM fuel cell, you can do that, but there's been no catalyst commercially available that shows any type of better performance than platinum. And what happens when you have less performance? So you wind up with two components, and replacing the platinum catalyst would be absolutely incredible for the technology. But, you know, in the decades of research that have gone into that, there's no better known catalyst material.
William, I would,
Yes.
sorry, Doctor, I would love to invite William to explain what borographing is for those of us that have never heard of it. And, you know, let's keep the conversation professional and educational and learn. William, if you're there, though, I would love to invite you to turn on your camera and mic because you lost me at that one.
Yeah. But the question then becomes efficiency, fuel utilization, and mass of the system. Because the number of kilograms that you store determines your range. And if you take a 10% hit in the fuel utilization, that decreases your range. So typically catalysts that aren't platinum based have an order of magnitude less performance than platinum based catalysts. So if you had something where you had very cheap electricity to generate very cheap hydrogen, that could be affordable. Or if the mass of your system was impacted, because if you have an order of magnitude less performance because your catalyst system isn't performing as well, then you have to size up the entire system. You need more surface area for the reaction. That increased surface area means you have to add more cells or even more stacks to the system. More stacks require more balance of plant. More balance of plant adds to your mass. So, and those are definitely, I know, critical critical considerations for getting things off the ground.
Yeah, very good point. Bill Spillane, if you're still on, Bill, I would love to invite you to turn your mic and camera on and say your comment. I know it was kind of probably more of a comment, but as somebody that's been on the side of developing a hydrogen powered aircraft and is also chairing HYSKY's Flying High Steering Committee, Bill, if you're still with us, I would love to invite you to come on.
Yeah, I'm here. You know, Doctor, earlier you said you showed the slide where the recoverability of the platinum isn't a huge market and the VCs don't love it, right? But when you're taking apart these stacks, you're right in the middle of what everybody in the entire industry is doing, and you're going to see it. You actually see more than all the individual fuel cell manufacturers do, unless they went and bought someone else's stack that got their hands on it, took it apart and did their own analysis. Right? So you will see what broke, what was close to breaking, what should be designed better, all of these things, and you can run an optimization analysis on it. So I would say don't sleep on that aspect of where your company is, and you have a different market to go sell your services to. So as a quick example of it was a hydrogen fuel cell company, a small one. They were simply just a test lab for everybody else. And they ended up testing different areas for each company. And they saw what was good at all of them and said, well, why don't we just make our own? And they ended up making their own and being acquired for a lot of money, right? Because they took the best of all of it and then just built their own stack. And you are essentially doing that, which is good, right? You don't have to do something totally new, but you can do it that way.
Excellent and interesting point. And yeah, to that end too. I mean, we're also happy to help work with benchmarking or any other services we could help to provide to anyone who's in the call here too. So I think that's an excellent point, because we certainly do see a few interesting things here. Yeah.
I bet you do. I really appreciate Bill's feedback. One of the pictures when I was showing aviation companies earlier, Bill was the COO of that company for quite a while, led a lot of what they were doing until, I don't know, 6 to 8 months ago-ish, 8 months ago, I think. So he's got a lot of hands-on experience from the aviation side. I would also say, just kind of words of encouragement to your team. This is probably one of our least attended webinars in 2 years, but don't fret, because you guys are really early on. Hydrogen aviation is really early on in general. HYSKY is really early on trying to forge this community. But this will go on YouTube, and I guarantee you people are going to go back and watch this and be like, wait, they were looking at this a long time ago. So you'll kind of have that timestamp to show that you were very early on. Excuse me, William, you're here. Did you hear me calling on you earlier?
I did. I had to try to figure out how to get my mic to work. Sorry. Yes, well, I would like to say that we're using graphene and borographene and other derivatives.
Could you tell us who we is, so that to
Oh,
let everybody know where you're
I
from,
see.
who you're with?
Sorry, I'm Dr. Rican, and I work in material science, and been working with graphene for almost 20 years. And we have been using graphene to replace platinum at every single point that we can, because not only because of the cost of platinum, but it's simply just too difficult to get a hold of. So we've been replacing platinum massively in every one of our projects by doping graphene in various ways.
Yeah,
And our graphene can mostly outperform or perform equivalencies to platinum doped materials. So we would be happy to prove that,
yeah.
because obviously you are working directly with platinum and you need proof, and that is perfectly fine for me.
Well, sure. If you want to send some
I
samples, we can help you do some kinetic benchmarking of that. And if you
I
haven't,
accept the challenge.
yeah, and if you have enough material to make an MEA, we could throw it on the test station and see how long it takes to degrade.
I'd be very happy to work with you on that.
Yeah,
So I see your email earlier, so I'll send you an email directly from my university, so we can keep in touch.
yeah, thank you. Nice.
Okay, I like that. Something that I thought maybe was negative turned into a positive.
Yeah. No, there's a whole area of, trying to break through this whole cycle of platinum being the best catalyst, and it would be an absolute boon for the technology if that's possible. I'm not skeptical that it can't happen. It's just that there's been a lot of attempts to do that, and it's not an easy feat to, make something better than its incumbent.
Mhm.
Yeah.
But that's always true,
Yep.
especially the main elements in the periodic table.
Yeah. Yep. There's a lot of combinations of those too, so not to
Mhm.
not to discredit that either.
Yes.
And then going back to what you said, Danielle, I think we're very optimistic, about the market and whatnot. It's just, there's a lot of demonstration going on right now with this technology and in this application.
Yeah, and
Yeah.
I think it's too early to talk to aviation folks about recycling platinum because I just don't think they would have a need for that yet. However, and it's just kind of adding on to like what Bill and I were saying, when some of these companies, I'm just going to use Joby Aviation because they're the most known. That's the only reason I'm using them. And they're very well funded and funded by Toyota and folks like that, and they have flown with hydrogen. If they were, raising money and and they are also working towards getting aircraft certified, there is going to be a piece of that where their investors are very educated on aviation, and obviously there's that FAA piece. They're going to need to know, what does the maintenance look like? Do you have a plan for this? When does it fail? And they may not know the answer to that. I think that's where you come in, as being able to provide expertise. So you may be able to be a strategic partner in just being able to provide some of that life cycle data and almost be like the MRO, the maintenance, repair and overhaul of hydrogen aviation. So just think about that. And I'm guessing that's probably not an acronym you've heard before. Most people haven't. That's like in the aviation weeds, but it is a very lucrative business, and there will be a need for that. So, just kind of think about what that might look like. And I would just say, did kind of think about their
Yeah.
they may not get recycling of platinum yet, but they will get oil change. They will get MRO. They will get that part. So it's just kind of a reframe that I was thinking about as you were presenting.
Yeah. And, Department of Defense applications for these, there are niche applications for hydrogen fuel cells that are absolutely critical for some of the contested environments, different grid resiliency types of facets. So these systems become a non-zero amount after a while as well.
Yeah. Yeah, I agree. Let's see. Anurag has a comment. Oh, nope, sorry. He does, but also, no, Anurag, you were right, because you had two comments. So, Anurag, if you like to unmute, tell us who you are. By the way, I know who you guys are, but Dr. Stuckey may not. So, please tell him who you are and who you're with, and you may ask your comments. And then after that, we'll get to Dr. Fu, Dr. Richard Fu.
Hi, everyone. Thanks, Dr. Stuckey, for an excellent presentation. Very much and well needed topic. I'm in India, and basically we're working on the hydrogen markets in India, working out who are the interested parties. So we're working on the entire hydrogen value chain, from production to logistics to storage to basically anything you would talk about. And aviation, particularly UAVs and drones, are the key focus areas right now for a number of reasons. From your presentation, I would want to know if, the method which you use for recovery, is that method applicable for recovery from other sources as well?
I think other platinum containing components, spark plugs, catalytic converters, those kinds of things.
So it's applicable for those as well, right?
There's some carryover, I think, on the refinement process side. I'd say our process, as we're pursuing its R&D capability, really relates to the architecture of the hydrogen fuel cell.
Okay.
Yeah.
Okay. But you haven't implemented.
We haven't
Sorry.
tried with other materials yet at this point, or other catalysts. Yeah, other catalyst systems that you'd find in like a catalytic converter at this point.
Right. I was checking where else platinum is used, and it works out that there are a large number of industries where it is used apart from FCs, and where recycling also could be useful. Yeah. And could you also just briefly describe what happens to the NWCNT, the degradation which the NWCNT undergoes?
For the what component? I'm sorry.
I understand that the platinum is on the multi-wall carbon nanotubes, right?
Oh, okay, yeah.
Yeah.
Oh, that was just an old work. A lot of platinum gets in the modern catalyst for fuel cells is usually on some sort of carbon, somewhat graphitized, but it's a porous carbon, so it's a high surface area carbon, so it can either sit inside the pores, and the carbon's on order of microns, and your target platinum size is somewhere around 2 to 6 nanometers, right? So it's all highly dispersed. And then as you operate the fuel cell and you undergo these different changes to the catalyst surface, you wind up coarsening those particles, ripening them, and the active ones wind up getting to be 10 to 12 nanometers. And so that's where you're getting towards your end of life event for the stack itself. And that takes thousands upon thousands of hours. And so we're still talking about those relatively small particles on whatever the support is. Carbon nanotubes are more of the R&D type support. Whereas the different types of carbon blacks and carbons are what you would find commercially available. Yeah. So we're able to directly remove it from there in the hydrogen fuel cell by using our processes and our systems that will help to just directly remove that from those systems.
Understood. Well, thanks a lot.
Yeah, and the other kind of thought about lifetime with that platinum particle size, as you grow those platinum nanoparticles that are the catalyst, you start to decrease the efficiency, which increases your need for fuel or decreases your fuel utilization efficiency.
Exactly.
And everything goes fine until you get to a particle or you generate a hot spot inside the MEA. And that's typically what leads to the cell breaking, is you wind up with a hot spot somewhere along the surface. And that hot spot will actually create a pinhole in the membrane. And then the
Yeah.
hydrogen is able to directly cross over from one electrode to the other. And then that area just kind of grows. And then it affects the cell next to it and the cell next to it. And eventually the whole stack very quickly becomes unusable. Not in the matter of seconds, but you notice quickly the decreased output of the stack, and that leads to an end of life event. So the whole purpose of catching a fuel cell for doing refurbishment would be to allow those particles to ripen, because they're going to. And a lot of support research, like research on the supports, research on alloying platinum with other metals like cobalt, goes towards creating that surface stability during the operation. And so the renewal side that we're focused on is, say, when that particle hits 10 nanometers, we do our process, we inject material, we take those 10 nanometer particles, we bring them back to 8 or 7 nanometer particles. And that's how we would look at achieving lifetime extension before it gets to the point where you generate that hot spot and you wind up destroying the membrane inside that stack.
We've got 1 minute. I want to give Dr. Richard Fu from Southwest Research Institute a chance to ask his question. Hopefully it's quick.
Hi, Dr. Stuckey. Thanks so much for the interesting presentation. I'm really glad somebody's working on platinum recovery. So my question, I didn't fully understand the process you're using. Maybe that's the trade secret for you guys. But wanted to kind of understand what is the recovery rate of the platinum and how much energy is required per milligram of platinum?
Yeah, so our process definitely has a lot of proprietary aspects, but we are able to do an injection into the fuel cell stack with it fully assembled to then effectively drive the platinum directly off the electrode and flush it from the stack. And the yields we're seeing right now are consistently at 80% driving the platinum off the fuel cell MEA. And then the last part to that question, I think we have no upper bound to yield here, and we have some R&D areas that we're looking at in terms of, transport and whatnot that we think will actually be able to get that yield up to 100%.
Wow. Okay, well,
Or close to 100.
Yeah,
Thank you, Daniel.
99.99. There's never 100, right? Thank you
Yep.
so much, Dr. Stuckey. Thank you so much to the FC Renew team, and thank you all so much for joining. Again, keep an eye out for an invite to HYSKY Connect. And with that, everybody have an amazing week. If you're in Houston, I'll see you at Exponential. Thanks so much again, Dr. Stuckey.
Thank you for having me today. My pleasure.
You bet.